In section 8.1, we look at complex numbers. The basis for all complex numbers is a number that we call I, and I stands for an imaginary number. And the number I is the number square root of -1. Now, what do we mean when we say the square root of -1? So let's just think about what the square root of 25 is. Square root of 25 is 5, and this is because 5 squared is equal to 25. So when we say that the square root of -1 is equal to this number that we call I, what we're saying is that I squared is equal to -1, and you can see that here. And so you need to know the definition of the number I, which is I is the square root of -1. And you also need to know this very important fundamental fact about I, which is I squared is equal to -1. And this is a new number because prior to learning about this, there is no real number that you can square to get a negative, right? So just think, if you square a positive number like 3, you get 9. If you square a negative number like -3, you get -3 times -3, which is still positive 9. So there is no real number that you can square to get a negative. So this number I is truly a special number. Now, another consequence of defining this number that we call I is that we are now allowed to take square roots of negative numbers. And the way we take a square root of a negative number is that if you have the square root of -a, you can factor the negative out of the square root and it becomes I times radical a. And you can see that summarized here. Now let's just talk about why that's true. So if you think of the square root of -a, you can rewrite this as the square root of -1 times a. And if we break this apart using properties of radicals, we can think of that as the square root of -1 multiplied by the square root of a. But again, we know the square root of -1 is I, and so we can write this as I radical a. Let's take a look at some examples. In our first set of examples, we want to write each square root in terms of the number I. So in our first problem, we have the square root of -25. So using the property that we just discussed on the previous page, we can factor this negative out of the radical. Now when you do that, it becomes an I. So we get I times the square root of 25, but we know the square root of 25 is 5, and so that leaves us with I times 5, which can be rewritten as 5I. For the second problem, it's essentially the same thing. We have the square root of -49. If you factor the negative out of the radical, you get I times the square root of 49. And this is I times 7, which is 7I. Now, once you get used to this, you can skip all the work here. You can go directly to the result. But I just want to justify why it is what it is. For the next one, we have the square root of -12. So again, you can factor the negative out, so that becomes I times the square root of 12. And then we can do normal simplification of radicals, and that is going to give us I times 2 radical 3. And then one final thing that we do here is you can write this two different ways. You can write this as 2 radical 3 times I, or you can write this as 2I times radical 3. And out of the two, this is the preferred method, and the reason is because when you put the I after the radical, sometimes it'll look like the I is underneath the radical, and that's not the case. But if you put the I in front of the radical, you never have to worry about getting confused like that. And finally, for our last one here, we have the square root of -17. Here I can pull the negative out, and we get I radical 17. And then after that, there's really nothing else that can be done, and so this would be our answer. Next, let's talk about powers of I. So we know that I to the first power is equal to itself, so that's I. We know I to the second power is negative 1. That's true by definition. So what about I to the third power? Well, I to the third power can be thought of as I squared times I, right? And the reason for that is because if you have I squared times I to the 1, this would be I to the 2 plus 1, which would be I cubed. So all we're doing is taking that third power and breaking it apart. And then once we break it apart, we know that I squared is negative 1, and I to the 1 is I, and negative 1 times I is negative I. Likewise, I to the fourth power can be broken down into I squared times I squared, and that is negative 1 times negative 1, which is positive 1. Now, once you get to this point, you're going to repeat all these numbers as you take higher and higher powers of I. So let's just consider, for example, if you had I to the fifth power, I to the fifth power is I to the fourth power times I to the first power. But I to the fourth power is 1, so we get 1 times I, which is I. So we're just starting back here again. And I'll do one more. I to the sixth power can be thought of as I to the fourth power times I to the second power, which is 1 times negative 1, which is negative 1, and that's this one here. And so we keep going through these same 4 values anytime you take a power of I. So a power of I is always I, negative 1, negative I, or positive 1. So let's take a look at some examples. Now there are a couple of different ways to do this. I'm going to stay consistent with what your textbook does. So I to the 30th power, what we can do here to simplify this is we can write this as I squared to the 15th power. And that's because using properties of exponents, when you have a power to a power, you would multiply those powers. So 2 times 15 would be 30. Now the reason we do this is because we know I squared is negative 1. So this becomes negative 1 to the 15th power. And this is simply negative 1, right? If you multiply negative 1 by itself 15 times, you will get a negative, and it will be 1 because 1 times 1 times 1 times 1 times 1 is 1, right? For the second one here, we have I to the 11th power. Now, we can't do the same thing that we did here because 11 is an odd number. So what I'm going to do first is think of I to the 11th power as I to the 10th power times I to the first power, because 10 plus 1 is 11. And then from there, I to the 10th power can be thought of as I squared to the 5th power times I to the first power. But again, we know that I squared is negative 1, so this is negative 1 to the 5th power times I to the 1 is I, and negative 1 to the 5th power is negative 1 times I, and this is equal to negative I. And for our final example here, I to the 40th power, we can think of this as I squared to the 20th. I squared is negative 1, and negative 1 to the 20th power is positive 1. Now let's define complex numbers. A complex number is any number that can be put into the form a plus b times I, where a and b are real numbers and I is the square root of negative 1. When a number is written in this form, it is called the standard form for that complex number. The number a is what we call the real part of the complex number, and the number b is called the imaginary part of the complex number. So let's just take a look at a few examples of complex numbers. So one such example would be the number 2 plus 3i. So all I'm doing here is I'm picking a number for a and I'm picking a number for b. And in this case, I have chosen 2 and 3. So this is our complex number. The real part of this complex number is the number that is not multiplied by I. So that would be 2. And the imaginary part of this complex number would be the part that is multiplied by I. So that would be 3. So notice the imaginary part is not 3i, it's just 3. Some other examples of complex numbers. We don't always have nice numbers like 2 and 3. I could give you something like negative 1/2 plus radical 3 over 2 times I. That's a suitable complex number. I could give you something like negative 1.7 plus 3.2 times I. Or 5 minus I, right? That would be 5 minus 1i. And then a couple of special examples is I could give you a number like 6i. That's a complex number because 6i is the same as 0 plus 6i. And also a number like 3 is a complex number because 3 is the same as 3 plus 0i. Now these last two examples here are special examples of complex numbers. The first one, 6i, is what we would call a pure imaginary number. And the second one is what you would call a real number. So notice that real numbers are also complex numbers. In our next example, we're asked to find x and y if we know that 3x plus 4i is equal to 12 minus 8y times I. So the concept here is that if you have a complex number is equal to another complex number, their real and imaginary parts must be equal to each other. So for these two complex numbers, the real part on the left side is 3x. The real part on the right side is 12. So because of that, we know that 3x must be equal to 12. And that would mean that x is equal to 4. And for the imaginary part, we can see the imaginary part on the left side is the number 4, and the imaginary part on the right side is the number negative 8y. So 4 would have to be equal to negative 8y, and if you solve for y here by dividing both sides by negative 8, we end up getting y is equal to negative 1/2. Same situation for problem number 9. On the left-hand side, we have the real part is 4x minus 3. On the right-hand side, the real part is 5. So we know that 4x minus 3 must be equal to 5. And this means 4x would equal 8, which means x would be 2. And the imaginary part on the left side is 7. The imaginary part on the right side is 2y minus 1. And so 7 must be equal to 2y minus 1. Adding 1 to both sides and then dividing by 2, we end up getting y equals 4. So the main concept here is that two complex numbers can only be equal if their real and imaginary parts are equal to each other. Now let's take a look at some arithmetic with complex numbers. Here we are asked to either add or subtract as indicated. And so addition of complex numbers is easy enough. Now I have parentheses around each one. That's just to show you the first and second complex numbers. But when we go to do the math here, we can remove those parentheses. So we have 3 plus 4i plus 7 minus 6i. And adding complex numbers simply comes down to combining like terms. So 3 plus 7 here, that would be 10. And 4i take away 6i would be negative 2i. So adding complex numbers is a matter of simply combining like terms. For the next example, it's the same thing essentially. We have 7 plus 3i, but then we're subtracting, and that negative has to be distributed to each one of those. So this becomes minus 5 minus 6i. And if we combine like terms, we get 2 minus 3i. Same thing for the last problem. We have to distribute the negative here. So this is going to give us 5 minus 2i minus 9, and then minus negative 4i is positive 4i. Combining like terms, we end up with negative 4 plus 2i. So adding or subtracting complex numbers is simply a matter of combining like terms. Now let's talk about multiplication. To multiply two complex numbers such as 3 minus 4i and 2 plus 5i, the easiest way to describe this is to just use the FOIL procedure that you learn in algebra. So we're going to multiply 3 times 2, that would be 6, and then we'll multiply 3 times 5i, which would be positive 15i. Next we have negative 4i times 2, which is negative 8i. And finally, negative 4i times 5i is negative 20, and then I times I is I squared. Now we can simplify. We can do a couple of things here. First of all, 15i take away 8i is positive 7i. Don't forget we have a 6 in the beginning. And then negative 20i squared. Remember, I squared is negative 1. So this is minus 20 times negative 1. And when I simplify this, I get 6 plus 7i plus 20, right? Because negative 20 times negative 1 is positive 20. And combining like terms there, we get 26 plus 7i. The second problem is actually even a little bit simpler. Here we have 2i multiplied by 4 minus 6i. What we need to do here is distribute the 2i to each part. So 2i times 4 is 8i, and 2i times negative 6i is negative 12i squared. And then all that remains is to remember that I squared is negative 1. And so this becomes 8i minus 12 times negative 1, which is positive 12. Now this answer is correct, but let's remember that when a complex number is in standard form, the real part should be first, and the imaginary part should be second. And so we should rewrite this as 12 plus 8i. For the next example, we are asked to expand 3 plus 5i to the second power. So let's remember that when you square something, you need to multiply that thing by itself. And then from there, we use the FOIL procedure as described on the previous page. 3 times 3 is 9. 3 times 5i is positive 15i. 5i times 3 is positive 15i. And positive 5i times positive 5i is positive 25i squared. Simplifying, we have 9 plus 15i is plus 30i. And then we have plus 25 times I squared, and I squared we know is negative 1. And so we end up getting 9 plus 30i minus 25. And combining 9 minus 25, we have negative 16 plus 30i. And the next example is a little bit special. Here we are multiplying the complex number 2 minus 3i to the complex number 2 plus 3i. Now you can use the FOIL procedure just the same way, but when you do this, 2 times 2 is 4, 2 times 3i is positive 6i, negative 3i times 2 is negative 6i, and negative 3i times positive 3i is negative 9i squared. So what's significant about this is positive 6i and negative 6i cancel out. And we end up getting 4 minus 9 times I squared, which is negative 1. And this is 4 plus 9, which is 13. So this is a little bit special. The reason it's special is because 2 minus 3i and 2 plus 3i are what we call complex conjugates. Now, complex conjugates have the same real part. So you'll notice the real part of each of these numbers is positive 2, but they have opposite imaginary parts. So you can see the imaginary part of the first complex number is -3, and the imaginary part of the second one is +3. And when you multiply complex conjugates, the product of these complex conjugates is always a positive real number. Like you see that we got here, we got +13. So the i's cancel out when you multiply them. And they cancel out precisely because of what happened here. So let's take a look at this in more general terms. So the numbers a plus bi and a minus bi are called complex conjugates. So notice that they have the same real part and they have opposite imaginary parts. And one important property about complex conjugates is when you multiply them, you always get a squared plus b squared. Now, why is that? Well, if you go through the process, to multiply these complex numbers, we do a times a, which is a squared. Then we do a times negative bi and positive bi times a. And those give you negative abi and positive abi, which end up canceling each other out. And then finally, we have negative bi times positive bi, which is negative bi quantity squared, like you see here. Now, what happens next? Bi quantity squared is b squared I squared. I squared we know is -1, and negative b squared times -1 is positive b squared. So what does this mean? Well, it means that if you multiply complex conjugates, you can use this formula as a shortcut. So for example, if I asked you to multiply 5 plus 4i and 5 minus 4i, all we have to do is take the real part, which is 5, and square it, and then take the imaginary part, which is 4, and square it, and then just add those two numbers together. And so this would be 25 plus 16, which is 41. So if you know this trick about multiplying complex conjugates, it can save you from having to use the FOIL process. Now for our last two examples here, we're going to do some complex number division. So in the first one, we have the number 2 plus I divided by 3 minus 2i. And it's a little bit of a misnomer because we're not actually going to use division to do this. What we do is we employ the trick of multiplying the top and bottom of this fraction by the conjugate of the denominator. So 3 minus 2i is the number we have there. We're going to multiply by 3 plus 2i to both the top and the bottom. Now, why do we do this? Well, it's because in the bottom, when you multiply these together, these are complex conjugates. And so the answer here is going to be 3 squared plus 2 squared, which we know is 13. And then on top, you just have to FOIL. So 2 times 3 is 6. 2 times 2i is positive 4i. Positive I times positive 3 is positive 3i. And positive I times positive 2i is positive 2i squared. Doing the math here, we have 6 plus 7i. And then 2i squared is 2 times -1. So that just becomes -2. And so combining like terms, we have 4 plus 7i divided by 13. And now I'll just separate this into two parts so that we have our answer in standard form. So the answer is 4/13 plus 7/13 times I. And for our final example, it is essentially the same thing. However, sometimes students can get a little bit confused when you have something simple. So how do we divide these? Well, again, we don't divide. We are going to multiply the numerator and the denominator by the conjugate of the denominator. So let's remember that the number I is really 0 plus I. So its conjugate is going to be 0 minus I, which is just negative I. So what I'm going to do here is multiply the top and the bottom by negative I. Now when we do that, in the denominator we get negative I squared, and in the numerator we have to multiply negative I times 7, which is negative 7I, and also negative I times negative 4I, which is positive 4I squared. Now we'll just change I squared, right? Because we know I squared is negative 1. So this is negative 7I plus 4 times negative 1 divided by negative 1. And this is negative 4 minus 7I divided by 1. So all I did on top here is I switched these. And then negative 1 is 1. But we know that negative 4 minus 7I divided by 1 is simply negative 4 minus 7I.